one of the main concepts they talk about is half-life. So half-life as the name entails, this is half-life, as in the longevity of how something is going to be around, like how long it's going to be around for. Now half of that, that's half-life. At least that's how we can look at it. No? Okay, so now that we have an idea of what radioactivity is, the first concept that they talk about in the papers is half-life. This always comes. Somewhere, if in science, you find it around questions 18 and 19, that's paper 1. Then for PY's physics, you find it somewhere question 39, question 40. So what is half-life? Half-life is the time taken for half of a radioactive material to decay. So this is the time it takes for half of a radioactive material to decay. And these very radioactive materials like uranium-238, carbon-14, thorium and whatnot, they have half-lives, and scientists have actually discovered these half-lives. So using the half-life, we are able to tell how much of a radioactive substance will be left after some time. So the questions will look like this. Example. So it will be like this. Let's say a radioactive substance of, let's say for example, 64 grams has a half-life of, let's say, 10 minutes. How much of it will be left after, so since 10 minutes, let's say after 50 minutes. This is how most questions look like. So, a radioactive substance of 64 grams has a half-life of 10 minutes. How much of it will be left after 50 minutes? There are many ways of solving this. Some teachers will even give you formulae, but for me, I prefer to do it like this, a way that anyone can easily understand what is happening. So, we get the 64 grams. It's going, then we take it into the halves like this. 64 grams. Half of 64 is 32 grams, and half of 32 is 16 grams. Half of 16 grams is 8. Then half of 8 is going to be just 4 grams. Half of 4, 2 grams. Half of 2, 1 gram. We can even continue like that. So when you get the mass that you are given, and then you cut it into halves like this. After you do this, you get your half-life. So the half-life is 10 minutes. So in between 64 and 32, for 64 grams to become 32 grams, it's taking 10 minutes. 32 to 16, 10 minutes, 10 minutes, 10 minutes, 10 minutes, 10 minutes. This is easy to understand. If you understand the definition for half-life, the time taken for half of a radioactive material to decay, so it was 64. For it to become 32, the half-life 10, like that. Now the question is asking us how much will be left after 50 minutes. So let's just count the minutes up to when they reach 50. So this is 10, 20, 30, 40, 50. So after 50 minutes, it's going to be 2 grams. After 50 minutes, you have 2 grams. And this is how most of the questions on half-life come. But in addition to this, there's also the graph. Let me show you how the graph looks like. Okay, so the graph looks like this. And by the way, the graph is found in 5054, that is pure physics, question 38, 39, 40, somewhere there in paper 1. So study the graph below. What is the half-life of the substance? So on this side, you have the mass or counts per minute. I'll explain what counts per minute mean when we reach the question that has that. But how you deal with mass, what I did with D64, is what you can do with counts per minute. We'll get there, don't worry. Then at the bottom, we have what? Time. So how do you find the half-life of this? First of all, ask yourself, what is the total mass you have here? It's 30. What is half of 30? Half is 15. So from 15, you just draw a line like this, and then you go down. Your half-life is therefore 10 days. So just find half of the amount you're given there, draw a line, draw it like that, you have found your half-life. That's how easy it is with the graph. Let's do exam-based questions now. Okay, so here are some examples. 2025 group 1 GCE. This is science. So an industry buys 200 grams of a radioactive sample with a half-life of 5 years. How much of it will be left after 20 years? If you do this enough, you'll be able to know that I'm just supposed to have this maybe by 3 times, 4 times. So it shows it's at least 4 times somewhere there. What am I talking about? This. We get the 200 grams, the mass we are given, then start halving it. So half of 200 is 100. Half of 100 is 50. Half of 50 is 25. Then half of 25 is 12.5. This should be enough. Now, what is the half-life? 5 years. So 5, 5, 5, 5. Now the question is, how much of it will be left after 20 years? 5 plus 5, 10, plus 5, 15, plus 5, 20. So after 20 years, we will have 12.5 grams of the sample that was originally 200 grams. Then 2023 paper 1 GCE, same thing. So what are we given? Half-life 6,000 years. Then original mass of count rate, it's 80 counts per second. What is this count rate? So that machine you're seeing right there is called a Geiger counter. It's what is used to detect radioactivity, the emissions that are produced by a radioactive substance. So it has a meter where it shows, or where it reads, or it shows how much radioactivity it's receiving, and that radioactivity is measured in counts per second. So now let's get back to the question. So carbon-14 has a half-life of 6,000 years. If the original mass of the count rate of 80 counts per second, what would be the count rate 12,000 years later? Like I said before, we take the count rate per second the same way we take the mass. So we just take 80 CR for count rate, or maybe counts per second slash S. Again, having this will be 40 CS, 20 CS. Let's end up to 10 CS. That's just up to me to end up to 10. If you don't write enough of this, the years will show that maybe you're supposed to make it a bit longer. So what is the count rate? The half-life, 6,000. So here, 6,000 years to move from 80 to 40, 6,000 years to move from 40 to 20, 6,000 years from 20 to 10 counts per second. Now, what time are we given? 12,000 years later. So 6 plus 6, 12,000. 20 counts per second. So 2025 paper 1. The first one I solved, that was GCE. Now this one is internal. The half-life of an isotope Z is 7 days, and its initial mass is 42 grams. What mass of the isotope will remain after 21 days? As usual, you get the mass, 42, and then you start cutting it into halves, like this. half of 42, that should be 21 grams. Half of 21, that's then 0.5 grams. Then half of that, that should be 5.25. Let me just confirm. 42 divided by 2. Yes, divide by 2. 10.5 divided by 2. 5.25 grams. If I want, I can continue, but let's see if this will suffice. So we want to go as far as 21 days. So this is 7, 7, 7 as my half-life. So 7 plus 7, 14 plus 7, 21. So after 21 days, it will be 5.25 grams. Then 2022 paper 1. Given that the half-life of thoron is 2 seconds, how long will it take for the activity of thoron to be reduced to 1/64 of its initial value? So here we are talking about fractions. When you have a fraction like this, the whole is 1. So the whole number is 1. So now we have to be reducing this one up until we reach this point. So half, as usual, of 1 is 1/2. Half of 1/2 is 1/4. Half of 1/4 is 1/8. 1/16 up to, let's make space here, 1/32, 1/64. So half of this is that, like that. Then we put the 52s here, 52, 52, 52, 52, 52, 52, like that. So we have reached this point. The whole thing, presented by 1, has now been reduced to this fraction of it, 1/64. How many 52s has it taken for us to reach this point? This is 1, 2, 3, 4, 5, 6. So this is just 52 multiplied by 6, giving me 312 seconds. And this is how you deal with questions that have to talk about half-life. Most of them, you have to do halves like that, then put in the half-lives, and then just find what you want. Or for pure physics 5054, you'll be given a graph most of the time. For the graph, just look at the biggest number, like I showed you. If you have this, and then up here you have 20, so just look for 10, draw a line, then come back down. What you find down there is going to be your half-life. Half-life is coming in your exam. Good luck.